All right, well, good afternoon. We're going to continue here with our discussion of motion. And last day we were looking at position, velocity, and acceleration, but in one dimension. So now we want to look at what happens when an object is actually turning. So we're going to take a roller coaster. So let's say the roller coaster, let's say the track is flat. All right, then there's a big loop, and it continues along flat. And what I want to sketch here is a motion diagram. So I'm going to say, first of all, that the roller coaster is traveling at a constant speed. That means, let's say it starts here, and a small amount of time later, it's over here. And we'll say that time interval is delta t. And a little bit later, it's moved an equal distance. It's approximately at the bottom of the circle. And then it begins to turn and go around. The distance between these points is still the same, but now it's along an arc length versus a straight segment. Making it up to the top, and back down around, and then continuing off to the right. Okay, so a motion diagram, to complete our motion diagram, what we need to add here are velocity vectors. And since it's traveling at a constant speed, those velocity vectors are going to be constant length. So v1, v2, v3 is still just parallel to the trajectory itself, since it's just a straight line. And the velocity at 1 is really an average velocity here, as we're taking a sampling of where the object is at a given point, or over a given interval of time. Right now, as it starts to go up the loop, that velocity vector bends to point upwards slightly. Well, that v4, and keeps bending, so we got v5, v6. As it goes around the loop, that velocity vector is tangent to the loop, which has a radius of r. And then it makes it down to the bottom. We have v7, and then goes off to the right, v8. All right. Now, I've written at the top of the board here centripetal acceleration. So is the roller coaster accelerating? All right, there are two ways to accelerate. Does anyone know what those two ways to accelerate are? How can an object experience acceleration? Yes?
A force, gravity.
A force or gravity? Okay, what do you mean by that?
Force times mass equals acceleration.
All right, let's leave force out of it for the moment. In the sense that I like the force causes an object to accelerate. But let's just say, how do we know, though, if an object actually is accelerating, or what does acceleration really mean?
There's a change in velocity over time.
Change in velocity over time. And what is? what are the two ways you can change velocity?
Like, well, I think of inputting force.
All right, I see, okay. So force is what's, no, you're right. You need a force to accelerate, right? That is correct. Now when an object's accelerating, there's two ways that acceleration happens. Either you're changing the, what does the force do? If it acts parallel to the direction of motion, it causes the object to change its speed. So it either can change its speed, or change direction, yes. Change direction. Right, well, all right, the object isn't changing its speed, but it is changing its direction. So there is a legitimate acceleration that's taking place here on the loop, not on the track, but on the loop. All right, what is that acceleration? That acceleration is going to have a magnitude and a direction. Let's try to figure out the magnitude, or I should say the direction, first of all. So here I have V3. If I take V4 and slide it all the way down, so it's touching the tail of V3, I have V4. Now, what direction is that, as I go from 3 to 4, is the velocity vector bending? It's kind of twisting upwards. It's bending up, so it's changing in that direction. This vector right here is the change in V. Right? So that would correspond to the direction of acceleration, because acceleration, recall, is just change in velocity over a change in time. All right, and it keeps accelerating as it goes all the way around. So let's say V4, I take the V5 vector, I move it to the tail of V4. Whoops. It's more kind of flat like this. And this vector, which connects the two tips, is the change in velocity, which is kind of always pointing, towards the center as it goes around. That delta V is always pointing towards the center. So the velocity vector is bending towards the center. Now, we can make this argument a little bit more precise by letting that time interval go to 0. And then what we really have is a couple triangles here. So the first triangle that we have is, well, the triangle with base delta V, and the sides of it is V, with the subtending angle being theta. Theta, this angle right here. And then geometrically, as I go from 3 to 4, let's have another triangle where the side lengths are R, and the base is just really the arc length, which is approximately, as delta t gets smaller, V delta t. Okay, so now using similar triangles, we know that since the angles are the same, the vectors have bent by the same amount. I can write the ratio of the sides, delta V over V, has to equal, well, V delta t over R. If I rearrange this slightly by dividing by delta t and multiplying by V, I get delta V over delta t equals V squared over R. And this is the centripetal acceleration. So the centripetal acceleration equals V squared divided by R. and the direction is toward center. Okay, so this is the result that we're going to use. Let's try a little bit of an example here. All right, well, first of all, let's just illustrate this. All right, you know, as the roller coaster is at the bottom of the loop, its velocity vector, you can see, is always tangent to the loop. It's always bending. And what direction is it bending? Well, it's bending towards the center. So as it goes around and around, now the arrow represents the acceleration vector as the roller coaster goes around and around the loop. All right, so let's practice a little bit with our knowledge here of vectors. So let's imagine we're on a racetrack. Okay, and the racetrack has a long straight section, which then goes into a corner, and then there's another loop, and then there's kind of a sharp corner which takes you back to where you started. Now I'm going to say that this is a top-down view. Let's say that the race car driver is starting here, starts from rest, and speeds up at constant rate. All right, now let's look at again, let's pick a few points along the race car loop. Let's say, pick this point, speeding up, and let's say that after the third point there, the car travels at a constant speed. And then for the rest of the track, just maintains that constant speed. So later on it's here, it's here, then it's here, then it's here, and then it makes it back and it just keeps going around and around as it goes around the loop. So what I want you to sketch in your notebook are the acceleration vectors at each one of these points. Questions about this problem before I give you a chance to work on it. So what I'll do here is I'll circulate around, but I want you to work quietly. I want you to work quietly. I'm going to give you a moment to discuss it in about a couple minutes, but what does the acceleration vector look like at each of these points as the car goes around the track, remembering that the magnitude and the direction are important here. All right, so take a moment for this.